There you go. Okay, we didn't get all the way through chapter 2 last week, mostly because I was tired of lecturing and I was getting a sense that you were tired of listening to me. Which means it's going to be worse today because we're going to finish chapter 2 and then do 3 through 6, which fortunately very short chapters. But let me just say, Stephen Glass has a tremendous background as far as his actual analysis of software engineering and what works and what doesn't. One of the complaints you'll see in one of his facts is that a lot of what passes for conventional wisdom or best practices is not founded on actual research. It's founded on, well, that seems like a good idea, so I'm sure that will work. And he criticizes that a lot. Most, if you read carefully through his book, you'll see that most of his facts and his fallacies, he has multiple citations saying, here's where this was done. Here's where this is proven. So we're back to maintenance here, which is, this is important. Maintenance typically consumes about 60% of software costs. Therefore, maintenance is the most important life cycle phase. We don't think of that. We think, okay, analysis and requirements, and we're doing architecture and design, we're putting a team together, and we're coding, and we're doing software quality assurance, and we shipped! Yay! Which is great, except that over the course of its life for a given software system, whether it's an in-house software or a commercial product, most of the time and money will be spent on maintenance. And this is something I learned at Fannie Mae. A lot of organizations, corporations, government organizations, will spend 50 to 80% of their entire IT budget on maintaining existing systems. In fact, there was a big project when I was consulting at Fannie Mae 20 years ago. There was a big project to replace the existing IT systems with what was called the object factory. This was sort of an object framework for building applications. And part of the reason was that if you plot it out over time, they were on course within 3 years to have maintenance consume 100% of their IT budget. They're trying to find a way to get that number down so they can actually develop new systems instead of spending all their money simply keeping the old systems running. I like their Glass's quote, "Old hardware becomes obsolete. Old software goes into production every night." Now, as I said, there's a lot of old software systems that I tell you would still be running today 17 years later were it not for Y2K. There are a lot of systems that I know because I got dragged into Y2K, and having seen this not only at Fannie, but I got dragged into Y2K at some other companies as well. A lot of systems that they had tried to replace or re-engineer, and for whatever reason, the people trying to replace, re-engineer it just couldn't get the budget, couldn't get the staffing, and so on to get this done. And with Y2K, it's kind of like it's going to cost too much, and so they threw it out. And hey, it still works. I mean, we still work even without that system. Enhancement. Now, this is an interesting stat. And again, he's quoting actual space here. 60% of software maintenance is adding new features. Now that seems obvious for commercial applications, because that's how you stay current. We're adding new features, That's why you have various flavors of Android. That's why you go from iOS 10.0 to 11.0, and then 11.1, and then 11.2, and so on. Error correction is only 17%. Therefore, software maintenance is largely about adding new features to old software, not fixing it. So keep in mind, and particularly if you find yourself in an environment where you're working for an IT department in a company that's got existing systems, about a third of maintenance costs will be adding new features to existing software. If you're doing commercial applications, that percentage is actually going to be a lot higher. Mostly it's going to be, okay, here's a new set of features we want to add. About 7% fixing bugs, 18% adaptive maintenance. The systems are getting older. You're migrating. You have an application. One of the reasons why there's still 6.5% of desktops running Windows XPs because they have applications that work under XP that won't work under Windows 7 or Windows 8 or Windows 10. And/or they don't have anyone who understands the application well enough to upgrade it so it can work. Or they, in some cases, they've lost the source code. Trust me. You'll discover this. You'll go into environments where there are existing programs that perform critical tasks for the company in question, and the source code vanished somewhere. And the interesting thing for me is the 5% on preventive maintenance, which is basically paying down technical debt. In other words, this is fixing all the quick and dirty stuff that you did to get into production. And this is a hard thing to get management to pay for. It is, in my opinion, essential, but it's very hard to get them to pay for it. Maintenance is a solution, not a problem. It is, and this sort of ties in, I think, with his, let's see, ties in with 45. Better software engineering leads to more maintenance, not less. Why? The program is better written and better documented, it's going to live longer. And so it's going to be around longer. You know, Windows, I can still bring up a command prompt under Microsoft Windows and do stuff that I was doing under MS-DOS 20 years ago. That's not an argument that Windows is well written, but the point is that the better written a program is initially, the longer lifehood it is likely to have, therefore the more maintenance you're likely to have. Part of the goal here then, particularly when you're doing new systems, is to try and architect them and design them to allow change-outs. In other words, if you're trying to design a model of cars that you want to keep in production for a long time, make the interfaces with electronics and fuel and transmission simple and standard enough so that you can drop an entirely new type of engine in and continue to run. Possibly a weak example, but I think you get what I mean. If you're looking for a long lifetime for a product or an internal system, invest that little extra to make it thoughtfully well architected, and stuff will pay off down the road. I mentioned briefly one of the, from personal development, one of the things I'm proudest of was the architecture that we did for Pages. Because after we had shipped 1.0, this new thing, and we shipped it in March of '94, that summer there was this new buzz, this thing that was going to be called the web and HTML. And I actually had someone at Next say, guys should look into this. Said, I think with what you have, this actually fits well technically. And we looked at it and said, this is a piece of cake. And converted our desktop publishing system to a drag and drop WYSIWYG, what you see is what you get, web page editor. Never had to touch a line of HTML. You'd lay out your web page and press a button, it would spit out the HTML. We had that working at the start of '95. We were years ahead of everyone else, and that was the problem because we were also running out of money. And we took this to venture capitalists who all said, oh, what's this web stuff? We don't know what you're talking about. And if it's important, Microsoft's going to own all of it. But the fact that we had invested so much in really thinking deeply about the architecture made adding that feature a piece of cake. In fact, we did I think 4 releases in the first year with significant upgrades. 4? Did 1.1, which was a bug fix, 1.2, which had new features, 1.5 was web pages, 1.7 had distributed objects. We did that all within a little over a year. And it's because we had invested the time in the architecture. And of course, then we closed our doors because this was still all running on NextStep, and we'd saturated the market. That was a dead end. Anyway, so you need to look at maintenance as a solution. Architect well so stuff has a good long lifetime, and make sure you set up the infrastructure. Matthew and I were just talking about this, about some changes going on where he works. Make sure you set things up so that you can actually update the stuff you're doing. You have people who know what's going on. They have the maintenance is a more difficult task than development. Why? Because you do all the same things. If you're doing version 2.0, it's like, okay, we have to do our analysis, we have to figure out our requirements, what are the implications for architecture and design, and on top of all that, we have to know the current system well enough to make the changes. Now with commercial products, you almost always have someone there in-house. And multiple, I mean not individual, you have a team in-house who knows the product well to make the changes. But if you're in an organizational setting, and this is internal custom software, you may well have no one who understands fully the architecture of the existing system. And you're going to run into a real problem when you try to change it, because you're going to have to spend time figuring out what's going on. Back to the story I've told about, at Apple, where I was having to fix bugs and add features to this off-the-shelf package I bought the source code for. And the source code was so bad, I ended up throwing out this one subroutine and rewriting it from scratch because I couldn't fix it as it was. Those are things that are going to happen. So, we have challenges of finding a solution within the context of the existing design, figuring out what things they discovered along the way. Why did they do what they did? Say, well, why didn't they just do X? And like, golly, I'm going to do X. And you get halfway through doing X and you say, oh, that's why they didn't do X. It doesn't work. I just ran into the same roadblock they ran into. Otherwise, finding out the current design can't support, oh, well, we want to go from dealing with a million records to dealing with a billion records. Because we're now going to use this with the Internet of Things. We're going to talk stuff all over, and it's kind of like, you know what? There are places here where scaling just breaks down. The architecture just can't scale to those extra 3 orders of magnitude. An article which you guys read earlier on having a maintenance architect. That's designed primarily for organizations with internal systems. So, a well-designed, well-built system will require more maintenance in terms of enhancements and lifespan than a bad one. It'll also be nicer to enhance and maintain than a bad one, because doing to a bad one's a problem. Okay, Chapter 3, Quality, Section 1, Quality. Quality is a selection of I have tremendous respect for Robert Glass, but he gets a little incoherent through here. Some of you may have noticed that. He sort of contradicts himself 2 or 3 times here. Because first, he says, quality is a selection of attributes. He picks a set: portability, reliability, efficiency, human engineering, testability, understandability, modifiability. I think are all good. I have a set that I use, which you can map a lot of them directly across. Reliability, performance, functionality. For me, those are the 3 big. Reliability means, is it giving me unacceptable answers? Performance means, is it taking an unacceptably long time to get something done? Functionality means, is it not doing what I actually need it to do? But I still like Jerry Weinberg's comment. He simply says quality is some value to some person. And that's important to remember, is that quality depends entirely on who is defining it and what is important to them. Now, having said reliability is one of his attributes, he then says quality is not reliability. And I'm kind of like, I don't get what you're talking about here, Robert. He's sort of trying to have it both ways. Now here's my definition of reliability, but he's dealing with what some people think is reliability and what he thinks is reliability, and so he's sort of saying my reliability is good, other people's reliability is bad. This won't be on the midterm, don't worry about that. But it's good to know that reliability is important. There are errors that most programmers tend to make. Okay, who amongst us has not done the if A is assigned B as opposed to if A is equal to B? Okay, I've done that. I've done that in multiple languages, you know. And I always feel like an idiot when I find it's like, you know. So it can range from those type of common syntactic typos to deep errors that we tend to make. You know, you have off by one errors. Okay, I'm going over a list. Am I actually starting with the first one? Am I ending appropriately with the last one? Or have I accidentally dropped the first one or the last one? Or worse yet, am I going off the end of the list and picking up, again, you're in C or something like that, picking up random garbage out of memory and trying to process it. He talks specifically about the open source assertion that given enough eyes, all bugs are shallow. But this is one of the reasons why that isn't true. We all tend to make the same mistakes. So given enough eyes, it's kind of like, oh yeah, that looks fine to me. This is, for me, one of the reasons why, I've mentioned here before, one of my best debugging techniques is to drag someone else in and try to explain what I'm struggling with. Because as soon as I start doing it, you know, I told you, I get halfway through, it's like, never mind, go away. I just saw what I did. Even though I've looked at that code a dozen times, I didn't see it. As soon as I tried to explain it to someone, it's like, oops, now I know what the problem is. Errors tend to cluster. This is very interesting. He cites a number of studies that show that errors tend to be, it's sort of the Pareto rule. It's like 80% of the errors tend to be in 20% of the code base. And he doesn't have a clear reason why that is. My personal reason is because, remember, we've talked about the do not defer the difficult. You know, don't push off the hard problems. When we do that, the hard problems tend to live in very specific areas of our code. And if we've pushed off really dealing with them, then what you get is a syndrome where you run across, it's not behaving correctly. The functionality isn't there, it's doing something wrong, and so it's in this module. And that's where the hard problem is. And you get just enough done to fix that problem, and then the next round of testing goes, and look, you've got another bug there. It's like, oh, well, I actually didn't handle this case over here. And you're starting to do a piecemeal handling of the hard problem. And so this becomes a little chunk of code that just keeps generating errors for you because you haven't taken the time to go all the way through. So there is no single best approach to error removal. He basically says there is no silver bullet. And he's addressing people who say, you know, if you just do this, you know, if you just do pair programming, if you just use this coverage tool, if you just do that, you know, you'll eliminate most of your errors. Tracking down bugs, in my opinion, if anything, is even more intensely intellectual than writing code in the first place. Because even with the best tools, you're still having to build up that whole structure in your head as far as this is what's supposed to be happening. And if you don't have that built up enough, even with tools, even with checkpoints, even with step-by-step debuggers, which I think are just wonderful. And that, of course, makes me sound old because, of course, that was an innovation that came around after I was a professional programmer. There are no silver bullets. Testing is just tedious. And this gets back to Brooks' comment all the way back in Chapter 1. You expect it to somehow, it's going to drop off and stop. And it's like, no, it's just sort of, it's a glide path. It's like, no, still bugs, still bugs, still bugs, still bugs, still bugs, still bugs. Residual errors will always persist. The goal should be to minimize and eliminate severe errors. Standard thing, you defer. In assessing errors, you need to determine how severe are they, meaning what kind of impact will they have on a user. How frequent are they? How likely are they to occur? Those are two separate assessments. You can have an error that's relatively severe, but if it happens infrequently, it's kind of like, yeah, we can live with that. How many of you have gone through blue screens of death? Okay, you know. That's a pretty severe error. You can, you know, your whole computer decides to reboot itself, and you know, unless whatever applications you're using happen to be backing up stuff regularly, you've lost work and so on. But as long as it doesn't happen terribly often, it's like, well, you know, I can sort of live with that. On the other hand, an error that, like, you know, wipes your hard drive. That could be a very, very long-term error, but it's still unacceptable. On the other hand, if you have another type of error that, say, randomly replaces the @ sign with the number 2 while you're typing, and it's happening all the time, it's not severe, but it's annoying as all get out. So when you're assessing bugs, it's kind of like, how severe are they? How frequent are they? And then as you get close to ship, we've talked about deferring features. We also defer bugs to ship. So it's kind of like, okay, you know, we'll fix that in version 1.1, or maybe 1.2, or maybe 2.0. There are bugs in Microsoft Word that I've been dealing with for 20 years. Anyway, that's another story. Okay. Efficiency. Efficiency stems more from good design. This is actually an issue of a lot of controversy. And I actually quote, Don Knuth is often quoted, "Premature optimization is the root of all evil." Don, father of computer science, well, not father, close, was talking, at least I believe, primarily about code optimization. In other words, his standard thing is, you know, get it right first, then worry about optimizing it, except that you have to design in advance for optimization. It's possible to design yourself and code yourself into a cul-de-sac and have to back out and throw away the solution in order for it to be sufficiently optimized. There is a trade-off, and he talks about, I put my comment in here, I think he talks about it again in number 54. There's a memory code trade-off. This is less than it used to be because memory has become so cheap and you count on so much memory. If anything now, I think there's a certain danger in that we tend to put a lot of stuff into memory, and then we use a lot of processing time trying to figure out just where it is. But, for example, to go back to primitive days, Sundog, I had to do some simple trig in determining, because I basically was using 3D coordinates both in star maps and ship-to-ship fighting. Now, the 6502 processor was an 8-bit processor, no floating point, and so on. So I put together two very simple sine and cosine tables. I just did lookup. Didn't try to calculate sine and cosine. It's kind of like, okay, you know, if it's within this chunk, here's what I've got. So that's a trade-off that you will find in other circumstances, and even in very large-scale systems. Sometimes you preload everything. Again, for all of you who play games, difference between the time it takes to load the next level, where it's pulling it off the disk, versus procedurally generated, where it's being generated like a No Man's Sky on a real-time basis, and so on. He talks about higher order versus assembly, which is not a concern or question you hear from most people these days. Usually what I hear from today's is bytecode versus machine code. You know, it's a compiled bytecode, or it is a compiled machine code. And you're actually at about the same thing. With just-in-time compilers and stuff like that, a lot of bytecode systems can perform almost as well as stuff where you're compiling straight to machine language. So the key here is not, don't worry about it. The key here is to know that, look carefully at the tools you're using and see where it matters and what you're going to do. And why did I have 3 here? Oh, well. All we care about is 54 here. And 54 is, that's why, because I decided to pull that in there, but I didn't delete the earlier slide. So you can ignore that slide. And he talks about the trade-offs between size and time optimization, which we already talked about. This is his complaint about research. Many software researchers advocate rather than investigate. As a result, some advocated concepts are worth far less than their advocates believe, and there's a shortage of research to help identify what it isn't. There is a real risk in talking about software methodologies, practices, and so on, and saying, well, of course, if you do X, it will be better. It's not always better. And sometimes you need to say, well, let's actually try it. Let's try two different ways here. I was having a discussion over the break with Matthew. He was talking about some reorganization at his firm, and it's kind of like, oh, we want to do this, and this will be great, and we'll do this. And my attitude, being a hard-boiled cynic, was no. you really don't want to do that. And I can tell you what's going to happen, and it's going to be this. And I tend, what works in software? Small teams of really great people. I mean, that's 90% of it. Small teams of really great people, and it really doesn't matter once you've got that. You can pretty much pick, and then actually this may be one of his next, no, it's not one of his next, it's one of his fallacies. It really, once you have that, it doesn't matter that much what tools or methodologies or languages you use, other than the fact that make sure you're all in agreement with it and that it's appropriate for the domain, what you're doing. Because I can think of half a dozen programmers that could grab and say, okay, we're going to do an embedded system all in assembly language, on an 8K machine to accomplish this, and say, yeah, cool, we know what to do, and we divide it up, and okay, you're going to do this, and we need this interface, and so on. And we could all be unfamiliar with the assembly language or with the hardware, and we'd all figure it out. That's why people matter the most. What you see in a lot of the industry is the opposite. You see organizations that hire people that aren't that great, or sometimes are really not great at all, and they try to make up for it with tools and methodologies and techniques. And guess what? It doesn't work. It really doesn't. Okay. His fallacies. We're getting close to the end here, folks. Fallacy 1, you can't manage management. Okay, sorry about that. You can't manage what you measure. We manage things we can't measure all the time. We manage our kids. I'm not sure what the measurement is. Well, let's see. They went to bed at 9:02. We'll have to work on that. It's more like, close the door and be quiet. Much of software development is intellectual and sociology. It's hard to manage that. Or it's hard to measure that. Actually, it's hard to manage it as well. But the concept that you can measure stuff and then manage to that has, within software development, often has counterproductive results. For starters, as we've already talked about, a lot of the metrics we use are bad. I'm managing you. Okay, I expect you to produce 1,000 lines of code a month. So what are your 30 lines for today? And you sort of like, that's silly, that makes no sense. But that's what a lot of these approaches boil down to. And this is a book, I'll try to put out a link to this. This is an important book, and I find that very few people, even in the industry, know about it. It was, forward is by Mark Lister. It's published by Dorset House, which is the same publishing thing. Measuring and Managing Performance Organizations. It is actually, if I say philosophical, it'll sound like it's not too grounded. It is a very thoughtful approach to the counterproduction of trying to manage people to metrics. And basically, his conclusion is a formal proof of what Jerry Weinberg says, that which gets measured gets fudged. When you have metrics and you're managing to metrics, what do people do? They do whatever it takes to make themselves look good with those metrics. And if the metrics are truly predictive and useful, you end up with these big distortions. I already told you the classic story of companies that have tried to implement bug bounties, and you have developers deliberately introducing bugs, and then the QA person finds them, fixes them, they close the bug, and then the two of them split the bounty. That happens in a number of different ways. Fallacy 2, you can manage quality into a software product. No, it has to be beaten into it. And what he's talking about here is sort of the, there is no I in teamwork. Management stuff. Same thing DeMarco and Lister talked about. Recognize that you're dealing with grown-ups here. Quality. This is a quote from an article you should have already read, and this was at a financial company whose name you'd recognize, who had adopted some sort of management system. There was some brand name management thing, and the three big things were mood, sincerity, and commitment. And they honestly thought that, like I said, they were telling developers, mood, sincerity, commitment are everything, and with them we can accomplish everything. No, you can't. You need good developers who know what the hell they're doing. and they definitely didn't have that, as the rest of the memo shows. Mood, sincerity, and commitment won't help you build an airplane that flies. You need people with all the appropriate engineering skills who can work together and who can very carefully do all the quality assurance that you want to do on a plane before it takes off for the first time. Programming can and should be egoless. Again, psychology of computer programming. For those of you who like to read books, there's a Silver Anniversary edition. Pick it up and read it. The technology is even more archaic than what you find in Mythical Man Month. But Jerry was there ahead of everyone else. He even does and I think I mentioned this once, that he talks about you can't make a baby in 1 month with 9 women. He uses that analogy, and he published that 5 years before Brooks did Mythical Man Month. He promotes this idea in the book that programming should be egoless. I should be able to write my code and just put it up there and let you all attack it, and it doesn't bother me. And actually, Glass, having given this as a fallacy, sort of backs off and says, well, yeah, you need to be sort of tough and mature enough to allow good reviews and critiques of your code. But it's ego that drives us to excel. It's ego that drives us to, by golly, I'm going to write the best sort routine anyone has ever written. I have this whole new idea. I'm researching all the different sort algorithms, and I've got this idea that with partially sorted million record databases, if you do this, this, and this. I've quoted Adele Goldberg as saying only optimists build complex systems. There is that sense of ego that needs to drive us to do our best work. But you've got to be grown up enough to let people actually review your code and accept the criticisms they have. Tools and techniques, one size fits all. This gets back to what I've been saying. You start with a good group of people, and then you figure out what's the best set of tools. What's the best approach? Because that will vary from project to project. If I'm off writing a game by myself versus if I'm off working on the software that controls nuclear missiles. My methodologies, my approaches, the expertise I'm going to need, so on and so forth, are going to vary. This is why people matter most. Software needs more methodologies. As I point out here, and I know why he wrote this, that may sort of startle you a little, but trust me, there was a period of time there, from about the mid-'80s up through about 2000, where it's like, here's the new methodology of the month. I have probably the equivalent of a good bookshelf worth of texts that are talking about code Jordan and talking about rational unified process in UML and talk about went out for about half a dozen object-oriented methodologies. And you've got structured systems. You go back before object technology, you've got structured systems development. And I mean, it's like everyone was coming out with their own new methodology each month. That has settled down, and everyone sort of says, well, it's really a trade-off between you know, waterfall-ish and agile-ish, and then you can sort of fight over the details from there. Fallacy 6, to estimate cost and schedule, first estimate lines of code. I would like to think this is not done anymore, but I'm sure it is. It's like, just don't. And really, with the advent of object technology, where a key aspect is refactoring and re-architecting and saying, okay, I've built this, and if I do this, this, and this, I can collapse it down so my code base just shrank by 30%. And that's a good thing. Trying to use lines of code as a metric just makes no sense, period. Random test input is a good way to optimize testing. It says, you know, I've got something I'm testing, and I've got input, and I'm just going to use some sort of random input value generator to test it. That's fine, okay? There are statistical and mathematical problems with that, particularly if the state space is pretty large. Beyond that, what you need to do is think very carefully about, you need to do some serious white box testing. What are the boundary conditions for that, you know, over the state of the program? Everything in here is fine, everything out here is bad. You trace the boundaries, and that's where you want to do a lot of your testing to make sure that you've got those covered. He, of course, also objects to given enough eyeballs, all bugs are shallow. Basically says he's found no documentation that actually proves that's true. And he points out an interesting thing. Debugging is a tedious process, and it is seen within software engineering as sort of second class. Therefore, you've got an open source project where you have people self-selecting what they're working on. Having to say, oh gee, I'm going to take this list of 10 bugs and fix them. I mean, that's altruism for you, not being paid for it. If the bug is one that's bothering you, then you might go after it. But I've been startled over the years with certain, I'm thinking like Mozilla and so on, where I've seen bugs that crop up, and like I run into it 3 years later, and it's like, yeah, this bug's been open for the last 3 years. Like, why has no one fixed this? It's because, like, well, no one's assigned to fix it, and no one has volunteered to fix it. Fallacy 9 is sort of awkwardly worded. What he's basically saying is trying to make the decision as to whether or not to continue to maintain or replace an existing system can't be based solely on what you've spent on it to date. And the gist of what he says is because it may actually be a fairly stable system, and you may say, oh, no, we're doing fine, but you may be on the verge, remember the arc of engineering, you may be on the verge of sliding off the far end. Or vice versa. You may say, yeah, we want to replace this because, you know, we're spending X amount of money. It's like, you know, you have to ask yourself how much money you're going to spend with the new system. Again, a lot of the failed projects I worked on, you have these extensive return on investment, which almost always is keyword for the number of people we can fire. We're going, you know, moving to the new system, and it's interesting how seldom that actually works out. That they don't actually get their return on investment. This was an interesting one, and I like this. He says you teach people how to program. The fallacy is you teach people how to program by showing them how to write programs. He said, for the most part, you don't teach people to read by showing them how to write. You don't teach them a language by showing them how to write it. You start by teaching them how to read it. And he makes an argument, which I think is actually a fairly cogent argument, that it might be a good thing to start people, non-programmers, out with growingly complex samples of code and teaching them how to read it. And I agree with him on a couple of reasons. One is I think that could be a very effective pedagogical approach. And second, guess what, folks? 90% of the work you do out there in the field is going to be reading someone else's code. It's like, I just got assigned to this project, I've got to come up to speed, I've got to read this. there actually are some books, a few books that address code samples. I don't know how many books are out there that actually talk about learning how to read other people's code. You tend to learn that through trial and effort and often desperation. It's like, oh my gosh, you know, what did this person do? And that's the end of that lecture. Are there any questions? I probably should have been asking for feedback through all those, but I figured you probably weren't getting out the driving this on. Any questions at this point? Any questions about the midterm? Any questions about your projects, about your assignments? I know some of you occasionally miss deadlines on some of the stuff. Just drop me an email. I tend to be fairly mellow about that. Like I said, as I said at the very start of the class, my intent here is to actually teach you. It's not to, you know, weed you out or to give you really tough stuff or so on. You're all seniors. You've got enough to worry about. My intent here really is to prepare you, as I've said time and again, for what it's going to be like to be out there in the real world, in real world software engineering. And I want this stuff just to sort of be ingrained in you by the time you leave this class, so that when it starts to crop up, you can say, oh my gosh, wait, I've heard this before. They're asking us to do what? I know how this ends and it's not pretty. And then you get to make the decisions. As I've said, it's kind of like, do you try and steer the ship off course? Do you hit the light post or whatever? No questions?